Hello, welcome to the webinar Basic of Vibration Analysis on Machines and Drives. My name is Peter Schreiweis from the IMC Test and Measurement, and I work for more than 20 years by the IMC Test and Measurement, and I have many projects in noise and vibration analysis. Today, I sent you from my home office this webinar because I have COVID and I can't go to our IMC film studio. Okay, let us start. We will start with the first question, what are vibrations? Vibrations are rotating or reciprocation oscillation of components or machines. How we can characterize vibrations? Here on the left picture, we see a sinus oscillation, a single sinus oscillation. And when we want to characterize this oscillation, we have the amplitude A, we have a phase angle phi, and we have the period of duration or the frequency, that is the reciprocal of the t. And the function of this of a sinus oscillation is like the formula that here stands. What else for oscillation we have? Periodic oscillation. Periodic vibration are oscillations that repeat themselves after a given time. And random oscillation. Random oscillations are not deterministic, which means that future behavior cannot be predicted. How we can measure vibration? Normally, we will measure vibration by accelerometers. And accelerometers are most commonly used for vibration measurement. This works, the accelerometer works as a spring mass to generate a force that comes from the vibration, and this force is proportional to the vibration acceleration and is converted into an electrical voltage or current via a piezo crystal and a measuring amplifier. So we have here the picture of an accelerometer with an included measuring amplifier. And this charge amplifier will be powered by a constant current, typical 4 milliampere. And we call this CCP, constant current power, IEPE or ICP. And this is all the same technique. Via a coax cable, we send the power and the information over this two-wire cable. And this cable length may be up to 100 meters. So it is also easy to connect a sensor that is not direct by the measure system. In the vibration analysis, questions are often raised converting velocity, concerning velocity and displacement. Accelerations, velocity, and displacements are closely related and can be transferred by mathematical integration and differentiation. Like here you see, from the displacement with the calculation, with the differentiation, you come to the velocity, and then you come to an acceleration. By integration and double integration, you come from the acceleration over the velocity to the displacement. Acceleration we measure in meter per square second or in g. 1 g is 9.81 meter per square second. And when do you want to calculate this in dB? Please take this formula, and so you can calculate the values in dB. The velocity is meter per second or millimeter per second or inch per second. Here you have also the function for a calculation in dB, as well as the displacement. Displacement we will measure in millimeter or inch, and you can also calculate this in dB. The harmonic analysis. The harmonic analysis is from Baron Fourier, a French mathematician and physics, and he said generally the presentation of periodic functions by assume of sinus and cosinus terms. Each oscillation can be determined by the time domain as well as by the frequency domain, and we call this spectral function or frequency spectrum. The formula you see here, we don't want to look to this formula, but the function E pi minus g omega t, it is in cosinus omega t and in sinus omega t. And then we can create a discrete frequency transformation. But I want to just show you how does this work and give you an idea of this. And here I start I'm the famous dialogue with the Fourier transformation and the Fourier series. We have here our time domain. In the time domain, I create a single sinus signal by an amplitude of 5 and a frequency of 5. Then we get this result. And when we transform this into the frequency domain, we see, okay, here I will change this to 100 Hertz. Here we see it 5 Hertz with the amplitude of 5. That is the same analysis, the same side of this time domain signal. When I add in DC signal, then I find this DC signal in the frequency domain by 0 Hertz. When I add some more frequencies, like a frequency of 11 Hertz with an amplitude of 11, 13 Hertz, 21 or 23 Hertz, you see here the time domain of these signals. But in the time domain, you can't see any frequencies more. You can't calculate it without the calculation of Baron von Fourier. And when we look into our time domain, in our frequency domain, We see here it is the amplitude 5 by 5 Hertz, 11, 30, 21, 23. We find all frequency that we generate. Mr. Fourier has also Fourier series, and when I'm looking to a Fourier series of a rectangle, that is this formula what we see here, and I have only 7 up to the 7th frequency, then I have a rectangle like this. But when I change this in, for instance, 21, then we see that we go nearer and nearer to a rectangle. And then I take 999, and it looks absolutely like a rectangle. We can this also make for a triangle or for a sawtooth. That is the same formulas, or like the same formulas as for a rectangle. And yes, we can also build a Fourier series with impulse. And so we see here that every 5 Hertz there's an impulse. And so we come back to Mr. Fourier and what he said, that we can build all a periodic signal by sinus and cosinus signals. Here this result for your documents. But when we work with Fourier analysis, or like an DFT or an FFT, a DFT is the discrete Fourier transformation and FFT is the fast Fourier transformation. Later on, I will say something about the fast Fourier transformation. But at first, we look on the requirements for the work with this analysis. At first, we need a fulfillment of Shannon sampling theorem, avoidance of leakage effect, and pay attention to the picket fences effect. Let us look what this is. The fulfillment of Shannon sampling theorem means that a signal must be sampled more than twice as fast. And here in our picture, we see in blue the correct frequency and in red the sampled frequency, and by the red points, we see the sample points. And when we look to this sample points, then we see, okay, that is another frequency like the blue color curve. And we call this aliasing. The amplitude, and it looks like a sinus, and the amplitude is that has the same value, but the frequency is wrong. And this arrow, we cannot be corrected when we have this digital. Oh, what can we do against this? We can take an analog low-pass filter, that will automatically connect the bandwidth with the sample frequency, that the bandwidth is on the half on the sample frequency. And then we call this anti-aliasing filter, that we don't get an aliasing in our signals. Avoidance of leakage effect. Another problem is the finite recording time. When we look to our formula, we see the formula is for minus infinite up to plus infinite. And when I measure this signal and I have not a complete sinus wave in our measurement, then it looks like this, and then we get jumps in the beginning and the end of the signal. And when we analyze this by the Fourier analysis, then we get frequency, wrong frequencies. There are lower and higher frequencies will be appear. The solution of this is we use window functions. A window function like Henning, Hamming, Flattop, or others, they make the start and the end of the measurement to 0. And then we have not these jumps. And we get a better result. At last, pay attention to the picket fences effect. The seemingly continuous spectrum is actually a picket fences of fixed frequency, like here in the picture, by 0, by 1 Hertz, 2 Hertz, 3, and so on. If there is a frequency between the picket fences, what will happen then? The signal information is not lost. That's the good thing. But it's calculated equally for higher and lower frequency bands. We call this the picket fences effect. The picket fences effect is the same as the leakage effect. The leakage effect is in the time domain. The picket fences effect is in the frequency domain. Also here is the solution. We use window functions. And so we have some results for analyzing with an FFT or an DFT. We need at first the fulfillment of Shannon sampling theorem. And we can't say this, and so we take anti-aliasing filter. And this is absolutely necessary. The avoidance of leakage effect and the pay attention of the picket fences effect, against this we take Windows function. And we take a look to some Windows function now here. We will start with a rectangle function. A rectangle function is we multiply the complete window with 1. Normally it is no a window function, but we call this rectangle. And when we look to our signal, when we get a result on the picket fences, then we get an amplitude of 100%. But when the frequency is between the pickets, then we get a damping of the amplitude. Like here you see, the amplitude is only 66% of the result. In which application we will take the rectangle function? We take the rectangle function when we know which frequency our sinus signal has. And for impulse signals. Impulse signals, they are by beginning of measurement, they are 0, and in the end of the measurement, they are also 0. And then it is the absolutely best a window function for this. For harmonic and stochastic signals, mostly we will take the Henning window function. And the Henning window function is like a half cosinus and another half cosinus, and it will start by 0. When we look to our picket fences, when the frequency is super for the analysis, we get also a result by 100%. When the frequency is between the pickets, then we get only 90% of the amplitude. That's much better than in rectangle window. And so we can say the Hanning function satisfactory amplitude and satisfactory frequency. But when we want to analyze absolute correct the amplitude, then we will take the flat top window. We see here we get 100% by a flat top window when the signal is on the picket fences, and we get 99.9% when it is between the pickets. And we take the flat top window for calibration and for a very accurate amplitude compensation. So the result, excellent amplitude, but not so exact frequency result. And this is a compromise. When we want to work from a DFT to an FFT, then we need samples by a power of 2. For instance, 128, 256, and so on and so on. And then we can build a faster analysis of the DFT. The result will be absolutely the same. And in 1965, the two mathematicians, US mathematicians, Cooley and Tukey, they developed a method to calculate this. And when you have 32,000 points to analyze this is in DFT, is the FFT 3,000 times faster than the DFT. And so we find in all our analysis softwares the FFT analysis, because it is much quicker than the DFT. So requirements for the work with DFT and analysis. Now I want to say we want to look to an example of the IMC wave vibration, and I go into our IMC wave software. I will start on the home page, and here I can give some metadata into my measurement. Then we go to the devices. Here I can choose the different devices, IMC devices, or we can also take a channel loader. Then we take the devices from our PC, or we have also for easy application the sound card what we can use. And there are also sound cards for within ICP, for ICP sensors. I load the channels and I have two analog inputs, an RPM and an accelerometer. The RPM, we can look here, the range is RPM, the unit. We need a filter, a sampling rate, and when we look to our accelerometer, we have the same. We see here the name, what we call it, the range meter per square second. The sampling rate, it is now here 10 kilohertz, and at least we find inline analysis. We find some functions to analyze this signal. By the plus button, we look now here to the IMC wave vibration. There we find the function vibration spectrum, FFT. And when we look in our FFT analysis, we see here, okay, that is my input channel, that is the name of my output channel. We analyze this as an RMS. We make no averaging of this data. I take now here in Henning window an overlap of 90%, no integration or differentiation. That we make here an integration of the accelerometer. Then we get the result for velocity. The sampling rate is 10 kilohertz on both sides, and we take 2000 samples. By 2000 samples, we get a resolution of 5 hertz. And then we can go to our next page. In the next page, we have here a channel balance. We can calibrate the input channels in the frequency domain. And we have a quick view window for measurement that is directly from IMC. And at last, we see here the customized page. And here that is the description of our measurement. Now we look into an electrical motor, and we have an RPM of 1800, a constant RPM. Here we see the level of the acceleration and the level of the velocity. Here's the time domain of the signal, and then we see here the frequency domain of the accelerometer, the frequency domain of the velocity, and here as well a color map for the measurement. And now we see this online for measure. So I will load now the next experiment for the next application, and I go back to the presentation. So since the industrial revolution, more and more work has been done by machines. Most of the machines are rotating machines with constant or variable speed. When analyzing machine with constant speed, we can use the well-known FFT analysis. In order to obtain exact vibration analysis during engine run-ups, the speed is divided into different speed classes. For example, when I have a run-up from 500 to 3500 RPMs, then I make, for instance, all 25 RPM a class for an FFT spectrum or an order spectrum. And then we get this color map or waterfall diagram, or as well we say also Campbell diagram. If in particular fast run-ups and run-downs, the machines are excite-made. The signal frequency within the speed classes change and the FFT spectrum is smeared. No exact vibration level can be determined. To obtain an amplitude accurate calculation, the time signal is resampled as a function of the speed. The order analysis by resampling is a conversion of the time domain to the angle domain. You can imagine it like an analog digital converter. You see the picture here, like an analog digital converter, which is triggered by an angel signal. You see here, by the rotation. And then, for instance, every 1 degree, I make a sample of this signal. And then when I have this signal in the angle domain, then you can also calculate this by an FFT and you get a fine order analysis. How to classify rotating machines? I will start with generators. Generators are components in power generation that convert kinetic energy into electrical energy. Electrical motor or engines are machines that convert a form of energy, whether chemical, electrical, hydraulic, pneumatic, or thermal, into a rotating kinetic energy. Then we have gearboxes. Gearboxes are hydraulic, pneumatic, and electromagnetic converters of torque, direction of the rotation, and the speed of the rotation. At last, we see turbomachineries. Turbomachinery converts energy between rotational energy into fluid energy by means of rotor blades, vanes, and blades. Examples include propellers or wind turbines, pumps or fans, as well as compressor engines, gas and steam turbines. Cause of vibrations on rotating machines. We will start with the forced vibration due to electromechanical interaction. With mechanical interaction, for example, gearing, interaction between impeller and the fluid. Then we can have on a rotating machine imbalance. Imbalance is when in a rotating body, the axis of rotation and the center of the mass of the axis do not correspond. Misalignment between the machine shafts. And here we see there is a typical frequency that is the double of the rotating frequency. By the imbalance, we see that is the simple rotating frequency. Wear and tear. When components reach the end of their service life due to wear, this is firstly indicated by low vibrations, later by higher vibrations, and finally the components will be destroyed. And we have critical frequencies and critical speeds. The dynamic vibrations includes the natural frequency of the components. As the result, the machine and its components can possibly be also destroyed. Okay, at first we take a look to an electrical motor. I take a three-phase synchron motor to look on typical frequencies, vibration frequencies. At first, we have an imbalance that is on all rotating machines possible. That is the first order. Then we have electromechanical interactions, and there is by three-phase, a motor is the third order, and mostly the fifth, the seventh, the ninth, and 11th, and so on. And we look to critical frequencies and critical speeds. I go back to our IMC Wave software, and here I have our new experiment. We measure now the accelerometer of a motor. We measure also the accelerometer of a motor and a gearbox. And when a motor, a gearbox, and a turbine work together, we have also results. We show these results on our pages and customized page. And now here we see, okay, we have only the electrical motor, and I will start this measurement. And we have here the additional orders, what I say. We see here the critical RPMs or the critical frequencies by a run up of this motor. Here's the speed, and here are critical frequencies. Here is the color map for a run up. We display this about the RPM. Here we have the spectrum. Here we have the FFT spectrum, here the order spectrum, and here also a run up by FFT spectrum. When we look to a gearbox, by a gearbox, yes, we can also have imbalance, but mechanical interaction and gearing, in our example, I will say, okay, we have the 15th and the 30th order. And yes, about these orders, there can also critical frequency or critical speeds. And when we add this with the motor, then we see our spectrum, the signals of the motor and the vibration of the gearboxes. We can also look here in our measurement. We have the motor and the gearbox. We have the run up. I will start again. We see here the 15th and the 30th order. And here the critical frequency of the motor are the red and the blue color, and the red dotted and the blue color dotted channel are the 15th and the 30th order of the gearbox. At last, we will also look to our turbine, and the turbine have an interaction between an impeller and a fluid. And when the impeller has 7 blades, then we get the 7th order, the 14th, the 21st, and the 28th orders, like this here. And when we build this together, then our spectrum change in all frequency and all orders of the whole components. And we also will look here in our signal, and here we see the critical frequency also from the turbine. Okay, what can you accept from us? The IMSI-Wave software offers more than just NVH calculations. It provides holistic test results. In the development area, additional measurement variables are often required in addition to the vibration variables. In addition, the sound and vibrations, the IMSI measure system can also record temperature, force, torques, strain gauges, GPS data, and much more channels. Signals that come from vehicle buses, like a CAN bus, or from a train bus, we can directly measure with our system, and you get synchronized data between it. And in the end, you can create meaningful results and calculate this also in real time. Do you have some questions or suggestions? I look. You can send me some information. I have a question. Is it possible to do envelope analysis with an IMC-Wave software? The envelope analysis, yes, this is to look on amplitude modulation of the signals. And we can add this in the IMC-Wave vibration analyzer. There we can analyze also envelope signals. Do you have more questions? I talked before about the anti-aliasing filter. All IMC measure systems has an anti-aliasing filter before it make a digital. And so the problems of aliasing you don't get with the IMC systems. Okay, I see there's no more questions. And now I'm ready for my presentation. At last, I will say, if you have any more questions, send me an email. The email address will pop up in a moment.